So our next presentation is from Colin Warren. Colin is has a mechanical engineering degree with a minor in physics from Washington State University. Go Cougs. Okay, yeah. Not easy for me to say go Cougs because I'm a former dog. So that was not easy. So he's presently now, while at Wazoo, he led a team that developed the hardware for Washington State University's first satellite to space. And he's now an associate propulsion component engineer at Maxar Technologies in Palo Alto, California.
Awesome. All right. Well, thank you very much. Glad to be here today. Thanks for coming. I'll caveat that though I work for Maxar, I'm glad to, at least because, well, for legal reasons, I want to put the disclaimer out that at least a lot of the thoughts that I'm presenting today are thoughts I've presented to internally within Maxar. And part of the reason putting on the conversation we're having today is that there are some ideas that I thought that I was surprised that Maxar was not as familiar with. So a lot of these slides are me kind of going through and talking about the ideas that was talked a lot about in this field, but are not as, I guess, communicated within, I guess, the rest of the commercial industry. But I'll caveat all this stating that, there'll be a lot of me talking about the applications between the ideas that are being talked about here today and, some potential commercial applications that are synergistic with, the interstellar probes. But I want to caveat that, these are my thoughts about how we can have, some combination between the ideas here and commercial industry. These are not Maxar deemed slides. So all opinions are my own. So a lot of this, given a lot of the conversations we had beforehand, this is not going to be news really to people. Again, kind of the intent for these slides was really to get a lot of my coworkers up to speed on some of the ideas that I saw presented here. So a lot of this will seem pretty straightforward. It's not going to be any, anything super new to people here. But I think the particular thing I'm trying to hit home is that we have this fundamental idea that there are spacecraft performances available if you leave your power source behind. That's being looked at for interstellar applications. That same idea has applications for many other mission profiles outside of, interstellar applications. I'll talk through one here today about a project that Maxar is working on. We'll kind of talk through the details there. And then, working through these slides a little bit more. And then once we kind of talk through kind of the mission, what's the potential mission profile of applying the beam, at least some of these beamed energy applications to a mission profile that Maxar is interested in. We'll talk about that a bit, and then, okay, great. This is a mission profile we're interested in. What's the path forward for looking developing the actual technologies that we need to make something like this happen? So that's kind of the overview. Without further ado, we'll jump into it. Taking it all the way the steps back. Okay, so we say this phrase a lot about, you get crazy, you get really good spacecraft power performances behind, enabled if you leave your power source behind. What's kind of the math that goes into, making statements like that? So the first fundamental, this should be probably pretty straightforward for most people here, but for those of you who haven't, at least seen the equations kind of written out, for propulsion systems that use reaction mass, it all comes down to the rocket equation at the top here, where you can, from the exhaust velocity and the delta V required you need for a mission, you can figure out, okay, what payload mass fraction can you get from, that given mission profile. Okay, from there, if you know your exhaust velocity, you can calculate the exhaust velocity as a function of the potential energy that's being converted into the kinetic energy. As that's fundamentally what a propulsion system's doing is, at least for reaction mass, taking potential energy, converting it to kinetic energy. You can calculate from every single known power source that we currently know through known physics. What's the maximum specific energy you can get from like a chemical reaction versus a fission reaction and a fusion reaction, even antimatter. You can take those joules per kilogram and then plug that into equation 3 to get what's the energy you get per mass for a given energy source. You can get the maximum theoretical exhaust velocity from that. You can take that exhaust velocity, plug that into your rocket equation, and that allows you to determine for given mission profiles, okay, what is the optimal, the optimistic best case scenario spacecraft mass fraction you can get for a given energy source. So, this is, these are all the missions, but to kind of walk through the different power sources and the different energy mission profiles, as it can be straightforward. We use a lot of chemical propulsion and fission systems. Chemical propulsion is what we use for a lot of the traditional, low Earth orbit to Mars, transfer orbits. You can see here that optimistically, if you were able to convert all of your chemical system, you get about 50%. Nuclear options, of course, scale better. As you go to, mission profiles that require more delta V, like a 45-day Mars transfer orbit, or a lot of the mission profiles we're interested in, the different, the 100-year, multi-decade flyby missions. You can see that as we plug in the different theoretical specific energies into get your maximum exhaust velocity, that there are specific, there's basically, there's only so many energy sources that can achieve given mission profiles. So you can see off to the left, okay, all of them can basically allow you to do low Earth orbit to Mars. But as you go further right to something like a 13-year Alpha Centauri flyby, really, if you're carrying your power source on board, you can't achieve those mission profiles. There's conversations around, okay, well, if you get an antimatter, there might be some hope for antimatter annihilation. There's a strong caveat that I don't know is, I guess I don't see, talked a whole lot about in the industry. If you look at a lot of antimatter propulsion systems, a lot of them tend to be antimatter catalyzed reactions, because you have to really deal with the concept known as the Brillouin limit, which is basically the idea that the amount of energy it takes to store antimatter because of this limit is going to be, with very rare, very short exceptions, it's always going to be more than the amount of energy you can release from the actual annihilation. So the antimatter numbers here have to be, the optimistic antimatter numbers here have to really be taken with a grain of salt. But the kind of the takeaway from this is that there are, if you carry your power source on board, there are mission profiles that you cannot achieve. So that kind of leads you to leaving your power source behind, which has kind of been the theme for, many of the presentations here. So for those of you who are, maybe aren't as, obviously a lot of people here are familiar with the idea, but maybe for those of you watching at home, a similar analogy about beaming your power source. A lot of analogies can be drawn by what the sun does in order to provide power and propulsion for some of the other applications. So you have a ball of, of fusion that's combining, that's doing its fusion thing. It's emitting the electromagnetic radiation onto, out into the universe, and you can capture that energy and use it for propulsion, either by capturing that energy through a solar photovoltaic cell and convert that energy into an ion engine, or you can use that photon energy directly into a solar sail. So you have fusion source, electromagnetically beaming energy, and you can capture that energy either through a solar sail or an ion engine. Exact same analogy applies with directed energy. You can take instead of a universe provided power source, you're using a human provided power source to beam energy into two different mediums. You can use it to either, beam right to a laser sail. You can beam it to a photovoltaic cell that's optimized for a given wavelength into the ion engine. And then, of course, as has been presented by a lot of the researchers here at Montreal, you can use both, or you can use the laser concept to also thermally heat up a rocket engine that way as another means of propulsion. So kind of recapping all of that, there are limits to carrying your propulsion on board. Here are the different methods if you want to start beaming your power, about conceptually how you start thinking about that. So that's, okay, those are the concepts about where you go about harnessing that energy from your beam power. And so, okay, great. There's beamed energy, awesome. So now you can start thinking about how do I get around these limits. But of course, with any technology, there's no free lunch. A lot of the stuff we've talked about today, so I won't spend on it too much. But beam power, if you have an aperture of a certain size, as you go further away, the power that's being beamed, the flux or the power per unit area is going to spread out as you get further away from the beam. So that's one of the main limitations that they have to work around. This technology, again, because if you're beaming the power, you have to, from a man-made source, you really have to start thinking about the economics. So you want to have it, your beamed energy source in a place that's cheap. If you're not, then that's the recurring costs start to blow up. There's a couple ways of in getting around the diffraction limit. You can make your array size bigger. One way to do that is to obviously create one big laser. Another way, one big monolithic lens. Another way to do that is instead of using one big monolithic lens, you can create the array through a bunch of different sub-modules that you can spread out over a given area using this phased array concept that we've seen a lot of people here present previously. And in terms of the other, again, there's a trade space you have to explore here of, okay, if you have a beamed energy source, you want it in a place that's cheap. Currently, the place that's cheap also has other problems like the atmospheric perturbations that you have to deal with. So this is a common question, a common problem they have to get around. So one way you can really get around this problem is you're able to take this beam source and you can put it at different points at either lower altitudes or higher altitude, put it at higher altitudes to really help you mitigate the atmospheric problems that you're seeing if you were to keep it at a low station. And given the kind of the concept of operations where you're beaming those things in space, it's a little bit more straightforward to make an argument about placing beam energy station on something like a mountain versus some of the other applications where you might need to beam energy to more terrestrial applications where having it on a mountaintop might not make sense. So these are the trade-offs. They are there's things that are addressable. But this is basically, if you leave your power source behind, these are kind of the main first order concerns that you're really looking at that you have to really trade against. So kind of with that quick overview and kind of tied together, okay, this is kind of how, if you're not familiar with beamed energy, that was kind of the quick crash course to get you up to speed. But okay, if we're trading it against traditional propulsion applications, how does that propulsion system stack up compared to some of our other options? So a really good resource that kind of using it as a point design to show you what mission profiles are usable is a paper that was put out by Phil and Sheeran from MIT on, hey, if we start looking at, we're looking at, mission profiles that are, very expedited mission profiles to Mars or Jupiter. What are the system level performance parameters that you need to hit in order to, enable these certain mission profiles? Because, again, though I work at Maxar, this is not a Maxar opinion, but in order to kind of explain this concept to some of my coworkers, decided to talk within the Maxar framework of, okay, this mission profile, let's go ahead and show how we would enable something like a 45-day mission profile for one of our satellite buses, which is the power and propulsion element, to kind of give you a sense of, okay, this is a technology NASA's working on. We're using it for the moon, but they have lunar applications. How would we modify something like the power and propulsion element to, instead of, doing the 8-month, 6-month, trip times to Mars, how could we modify the power and propulsion element such that we could take advantage of the mission profiles that Phil and some of the MIT researchers have, taken a look at? So quick crash course for those of you who aren't familiar with the power and propulsion element. It's basically the International Space Station for the moon. There's a couple components. There's the part that Maxar's working on, which is the power and propulsion part, which is the 50 kilowatts of solar electric propulsion and power that's going to be used to actually take the first stages of the lunar module to the moon. There's also the habitation and logistics outpost provided by Northrop Grumman. So that's the concept of operations is you have this bus. they'll take a 1-year electric orbit raising operation to get from nominally low Earth orbit around to the moon, and then it will basically sit there and allow all the other modules to start attaching to it. So here's some kind of the nominal publicly available performance numbers about here's how heavy the station the power propulsion element plus a notional the actual not the actual halo habitat, but how roughly order of magnitude, how heavy is this propulsion system, and how much propellant are we using to do these electric orbit operations. So we can take this given system and start asking ourselves, okay, this bus is already available. How do we modify it for the 45-day mission profile? So in order to do that, because you're carrying your power source on board, you have to use different equations as the previous energy sources. That there's a finite amount of propellant, or basically there's a finite amount of energy that you're carrying with your spacecraft. So you're using a potential energy is converted to kinetic energy. Because you're beaming your power, there's an energy per unit time. So you have to include the time component in your equation. So these are basically the formulas that you would end up needing to use in order to start analyzing different propulsion systems that are using different power sources, pulled from rocket propulsion elements, and then some of the basically the classic textbooks on electric propulsion on analyzing that. So you can take what's the specific mass of your power system? You can convert that to the characteristic velocity, which is just kind of a notional, the nominal exhaust velocity that's attainable by the power plant if it was converted directly to kinetic energy. From there, you can take your actual specific mass for your power plant, and then you can convert that to you can do the same thing about converting that to the actual payload mass fractions to actually start looking at the trade space here of, okay, if we want to achieve something like a 45-day mission profile for Mars, what are the different power sources that we can use? How do they kind of scale with one another? Are there certain power sources that enable this mission? Are there other ones that are there are other ones that are just fundamentally aren't going to enable, are fundamentally limited by the chemistry. So you can take those previous formulas. You can kind of do a literature search of, okay, what's the state of the art nuclear fission and solar power? What's their specific powers? What is the optimistic cases for those given? What are the optimistic cases for those specific powers? And then you can take those specific powers, you can plug it into basically the previous parameters shown for the 45-day Mars mission profile of, assuming a 60% propulsion efficiency and then roughly 78 kilometers per second. And then you can start asking yourselves, okay, if I'm using a nuclear fission system, what is the payload mass fraction achievable if I have a power source of this given power source for a given mass? If you take a look at the graphs, basically what the emerging story is that if you're looking at modifying the PPE bus for a 45-day mission profile, really your nuclear fission, that specific power source, it really doesn't have it really doesn't have the specific power you need to actually get significant spacecraft mass fractions that you need to get to Mars in 45 days. Really, what you're looking at is the solar power and the laser power connected with electric propulsion. The trade-offs between the two is that solar power, you're going to have really wide solar arrays. So there might be an engineering challenge that comes along with that. On the laser power side, you have a much smaller solar photovoltaic or a photovoltaic array. But then, of course, you have the other considerations, which we'll talk through on the next slide about the actual the cost of energy, and basically the cost of energy and those specific trade-offs there. So if we taking a look at the previous slide, okay, if we did the trade space of, okay, there are certain specific powers that, that you have to have a certain specific power in order to get a given payload mass fraction. Beamed energy scales a lot better compared to solar power and nuclear fission. Okay, let's start looking at the other trade-offs of actually switching to something like beam power. So again, taking the Sheeran paper, we actually pull out the numbers here. The actual power, the actual delta power, the beaming station power need the actual power that you need to put in, about 160 megawatts. So you can do the quick back of the envelope calculation about how much money in terms of energy cost that you need to do in order to perform this mission. Ends up being, a few tens of millions of dollars, which could be interesting to some shareholders. Then you can adjust, at least from the power and propulsion element, system parameters. You can start adjusting the actual, given that you need roughly you need these spacecraft mass fractions. How much xenon would I need to carry for this mission? How would I need to modify the 50 kilowatts needed to get to the 320 kilowatts propulsion power in order to perform this mission? Notionally, you would need to change from the airjet thrusters and the Busek thrusters that are currently on the system to some other ones that are being developed. There's maybe a concept forward here on taking some of the XR100s, which are the 100 kilowatt Hall thrusters, putting them on the back, and then basically taking technology that's being developed currently and modifying the PPE bus such that you can take advantage of these 45-day mission profiles. One caveat, though, is that as you do the propellant that you need in order to modify the PPE bus, if you take a look at that number for xenon, it ends up being about 30,000 liters of xenon that you need. For those of you who might have been paying attention to the price tag on that, that's not the cheapest. So there's a incentive here to if we're not the cheapest and trying to store 30,000 liters, not super straightforward. But in order to kind of get around this problem, if you're looking at this mission profile, there's an incentive for you to start looking at solid propellants here, as not only are they going to be cheaper, they'll be a little bit denser. The trade-off, of course, here is that the solid propellants, that's still a very early area of research. So that'll be something that you need to develop. But really, if you're looking at modifying, currently available commercial spacecraft to do the mission profiles that a lot of researchers are suggesting that we could do with electric propulsion, there's really a strong argument to start moving to stuff like solid propellant, just with the amount of mass that you need to fit into a given volume. So that's something that kind of came out from the literature search as we dove into the details a bit here. So something to consider there. The main thing, and Harry kind of touched on this a bit, and there was a lot of questions in the last section on the other big important subsystem. How much does it cost? Really, if you're looking at if you want it, we're taking all the research that's being talked about here today. Let's say we take these beamed energy stations and we want to start modifying the power propulsion element or other electric propulsion systems to do these mission profiles. What's one of the major blocks that's stopping us from doing that? Really, it's making these meter size arrays. The actual individual modules, you could probably hook them all up to do a basic test. But really, when you're starting to look at building kilometer-sized arrays in order to do the beaming, this is going to be the thing that this is basically this is the piece of technology that at least a lot of the commercial industry will be looking at, having to see that get a little bit more developed before we can really start, actually start using some of these high energy, these fast transit time mission profiles. seen in the literature, just because of how much currently it costs. Though it's trending in the right direction, but really the millions of elements and the the rough order of magnitude, tens of thousands of dollars right now is just not like this. The actual beaming station is kind of this is the critical path, the actual item that's really, I guess that the industry really needs to see developed more before we can start really enabling, start coupling the work that a lot of the interstellar research group is doing with the current spacecraft buses, like Maxar or Northrop, the actual electric propulsion systems. This is what we'll be, really paying attention to. So yeah, this is kind of the summary of the summary of the presentation of, okay, great crash course in beam power, why you're interested in that. Here's a point design. This is just one design. There may be other mission profiles that may be interesting. This is something where this is a very unexplored area that I think there definitely could be more researchers doing a trade against, exploring the trade space with not only, nuclear and solar. We showed the example of laser electric propulsion or your laser source. This is something that should be explored more, and I think we need a lot more help from academia to actually, start exploring different mission profiles and really, building up the literature base so that more people are familiar with, hey, coupling laser or beam power with other mission profiles. It does seem competitive compared to the other technologies. But yeah, at this point, these are kind of the overall technologies that we need to develop. Kind of the critical path ones are that laser phased array. And then once that's developed out, I think in parallel, you could probably do some ground demonstrations where you can, show that you can have a high power electric propulsion bus that can receive power from one of these arrays. But yeah, until that point, this is kind of the state of the art. This is what industry is looking. These are the particular technologies that industry, at least from the electric propulsion side, is looking to see developed. If you happen to be interested in these sort of mission profiles and or developing them, love to talk more. But yeah, currently, because companies like Maxar and Northrop Grumman aren't commercial, they're commercial companies. We really need to look to groups like the government and the government and civil programs to actually provide the funding to, if there is an interest, to actually provide the funding to enable the development, the actual development of the technologies in order to enable a mission profile like this. Yeah, thank you very much, and I guess we'll see if I left any time for questions.
Thanks, Colin, for the summary. You and I have spoken a lot about this, obviously, over the last couple of years. There is a major, I think a misconception is a proper word here that you were clarifying nicely here. Namely, if you want missions in the solar system at, say, the hundreds of kilometer per second range, you don't want to use a light reflector. You don't want to transfer momentum via photon exchange. What you want to do is match your exhaust speed to roughly the speed that you desire to achieve. And that's done in chemistry and has been for many, many decades. So some people, I think, have a misconception that you just take the laser rays that we're working on and shine them at a reflector. That's not the right way to go at all in the solar system. You can get much more mass to the target at the reasonable speeds you want because you're not going relativistic in the solar system. So I think it's a very important point. So if you go back one, to this, the cost, if you hold it there, I just point out that the cost of Apollo in today's dollars is about $300 billion, which is the 10K comes from our quote to you at quantity one. That's what it costs us to produce a sub-element at quantity one with no discounts. You're just multiplying that by 25 million elements. So even at today's dollars with quantity one, no discount, you're already not above Apollo in terms of cost. And I think that's another misconception is that people think interstellar is going to be cheap. I'm one who doesn't believe that, but and I know some others do.
Yeah, very much echo that. And I think one of the main things, because this is basically the pitch deck I've been having to pass around internally within Maxar to go, hey, this is something we should really explore. And one of the common questions are, because as a company, it's great, how much does it cost? the actual cost of energy, that's a pretty easy one, but very much the actual like getting a sense of rough order of magnitude on, okay, if Maxar were to build one of these stations, or if Maxar was to approach somebody else on building one of these stations, with the obvious caveat that this price tag is gonna, is trending down very quickly in the coming, decades. Maybe there's a point within the next 5 years for it's like, okay, this is, hundreds of billions of dollars. Maybe that price point to a potential customer is they're willing to buy it. I imagine not, but at least just getting a rough idea of here's where the state of the art is. Here's a rough order of magnitude of the fixed costs. So then we can start getting ideas around, okay, at what, if we start putting this idea in front of customers, or, commercial industry in general, like what price tag roughly are we looking at? And maybe we have a sense of how often we should be checking back in over time.
Yeah. Well, also, you end up with a launch facility for the same cost as Apollo, even in today's dollars, Quantity 1. And with that same facility, you can go interstellar, you can go through the solar system, get humans to Mars in 30 days. So then you have to think of how you amortize over the multimodal mission space. And that's really important. I think it's what's missing in this conversation.
Yeah. So I think it's very much I guess what the stakeholder involved, is that the amortization, is this something like in my head, this sort of price point? I would imagine a commercial company like Maxar would want to work with somebody like, NASA or DoD to do some of the initial missions to, that are more amenable to amortizing costs like this. And then, later on, any of the other customers can, kind of take advantage of that. Those other, the DoD and I guess NASA stakeholders that might be more willing to kind of front load those initial costs, kind of like they did with Apollo starting out.
Let's thank Colin.